Hello everyone, welcome back. So in this week's lessons, we're going to revisit the idea of working with agents and groups of agents or particle systems. Except this time our focus is going to be more on behaviors. So we're going to do this in a few parts. First, we're going to do a version of something we did in week 2. We're going to redevelop an agent object, and then we're going to talk about sort of steering behaviors for that agent. Then we're going to move to more of this idea of group behaviors, and we're going to implement some kind of a swarm, flock kind of behavior for our agents, both of which are very much inspired by the work of Craig Reynolds, who was a computer scientist in the 1980s, who developed these autonomous agent behaviors for simulations. And also the work of Dan Schiffman in The Nature of Code. So I'll be linking to both of these things down below. Much of what we're doing this week in terms of behaviors is very much derived from one of the chapters in Nature of Code. So if you want to go a little bit more in depth, you can also take a look at that book chapter. So let's dive right into it. Okay, so I've remixed just our blank sketch here on Glitch. So much of what we're going to do in this first part is going to be a recap of what we've already talked about when we covered vectors and agents. So we'll be rebuilding some of these functions rather than copy and paste from that week's example, and we're going to use this as a bit of a review. A lot of what we're doing in this week's lessons as well is kind of taking everything we've seen since week 1 and trying to eventually tie it all together into one final drawing machine idea. Okay, so let's start with defining an object that's going to represent an agent in our sketch. And one of the ways we can do this, there's many ways we could approach this. We could write a class, for example, to represent our agents. I chose to go a little bit, take a simpler approach here, and think of our agents just as these basic JavaScript objects. So the syntax to define a JavaScript object goes like this, right? We can define a variable, and then we use the curly brackets. And then inside the curly brackets, we get to define pairs, right? Where we have names and then values. And those become the attributes of the object we're creating. So we're going to say an agent is going to have a position. Now, for the sake of this example, I'm going to shorten position. I'm just going to call it POS, just POS, just so we have less typing to do. But we're going to understand this as position, and that's going to be a vector. And this vector, we're going to give our agents random starting coordinates, just to make things more interesting. So let's understand this to be position. It's just going to be a shorthand. We're going to do the same thing with velocity. So velocity is how fast are we moving and kind of in what direction, and that's also represented by a vector. Now the velocity, we're going to make it random, right, between -1 and 1, and that gives us a little push in a random direction to start with. And let's put a comment here that we understand vel, V-E-L, to be velocity, just short for velocity. And then in week 2, we talked about this concept of acceleration. And the acceleration is useful because it allows us to build velocity over time, right? So velocity is going to affect position over time. It's going to give us movement. And then acceleration is going to affect our velocity. And by having this acceleration concept, we are going to be able to add multiple, sometimes competing forces to our object. And we're going to use this to create some interesting behaviors. So the acceleration is just going to be an empty vector, just 0 and 0. So what we've done here is created a variable, an object called new agent. And then inside this object, we have three variables, right? POS, vel, and acceleration. And all 3 of them are vectors. So all our object is really, it's a little package for 3 quantities, 3 other objects. So it's just a way of bundling things together. So when this function is done, we're going to return this new agent we just created. And we're putting that inside a function just to keep our code organized and have some, clearly delimited sections in our code. We could have done the same thing up in setup here, but as our program gets more and more complex and the more lines of code we start to add, it helps to keep things in smaller building blocks. So that's why I decided to make this create agent function. So in setup, we're going to make our agent variable equal to create agent. Okay. Now, of course, if we run this code, nothing happens because all we've done is we've created this agent. It has quantities inside of it, but then we also have to manipulate them, do something with it. So the first thing we're going to do is let's put in some kind of drawing function for our agents. We're going to call it render because draw is already taken by our main draw loop here. So let's call this render agent. And the job of this render function is going to be take an agent and then draw it on the screen. So for our purposes now, we're going to draw our agents as little rectangles. Okay? And we're going to refine this down the road in future examples. So I'm going to use push and pop here because I intend to use translate to bring the origin to the position of my agent. And I can access this using agent.position.x and y. I'm also going to rotate the canvas to point in the direction my agent is heading. And I can get that information by looking at the velocity vector and then taking using the heading function that just calculates the angle of a vector. So the velocity is where we're going to be moving towards. Therefore, its angle, we can orient our object by rotating using that angle. And then let's just draw a little box here at 0, 0 and a little rectangle. I'm going to also set rectangle mode to center so that the center of this rectangle is also the center of my agent. And then in draw, we're actually going to call that function so we can see it happen. We're going to say render agent. And we get a little dude appearing over here. It's going to be different every time because we're getting random coordinates, right? And we get also a random velocity, so it's going to be pointing in a different direction also every time. Now, I want to talk briefly about something here. This could be a source of confusion. So we have a variable up here called agent, right? This is our global variable that contains our agent object. And then I also have a parameter here, and I've also called it agent. Okay. Now, these things are not necessarily the same. In this program, they are because I only have one agent. So when I pass the variable here to the function, it then takes on the name. It keeps the same name here, agent, inside the function. But I could have called this, I could have shortened this as well, called it something else, and it would still work. Okay. So these two are independent in a way. So whatever we pass, it happens to have the same name here. It happens to be called agent. When we pass it to this function, we could change the name here because whatever the parameter is, this is going to become the name for within the function. The idea here again to make a function for rendering is that down the road, if we have multiple agents, we can reuse that code with different agent objects, so they can all share the same drawing code. So we could decide to make it short here, just call it A, for example. But I find this hurts the readability of the code a little bit because now it's not as clear what we're doing, right? A versus agent. So that's why I chose to keep the same name. Just call it agent. Okay, so we're going to keep calling this agent. Currently, it turns out it's this, we only have one agent in our program, so it is the same throughout, right? This is the same object we're passing in here, and then it comes in here, and we keep calling it agent. But down the road, we're going to have hundreds of these, and it could be any of them getting passed to the function. So this is an important little distinction I want to make here. So back to the program here, it's not moving. So let's also program a little function that's going to apply our basic motion equation. So if we move an agent, what does it mean to move an agent? Well, we had defined in week 2 the basic idea for motion, right, was basically to say position is equal to position plus velocity. So if we have a position vector and a velocity vector, we add the two together. What the result is, we're moving the position by velocity. So if you want to translate that into code, this is how we can write it. We can say agent.pos, this is the position. We're going to add to that the agent's velocity. And I'm leaving the comments here just so we have a kind of a clearer understanding of what that line is doing. So let's call it move agent. Okay, so we can see our agent started to move now, and basically we're taking its velocity, adding it to the position over time. Okay. Now we're not using the acceleration yet, but let's just build it into our move function just to begin with. So before we add the velocity to the position, we're also going to increase the velocity over time. So whatever is inside the acceleration vector, we're going to add that to the velocity vector. So this is going to be velocity, right, equals velocity plus acceleration. And then at the end, when we're done, we're going to take the acceleration vector and we're going to multiply it by 0. And what that does, it just says the acceleration, right, is equal to itself times 0, which means it will just reset it to 0. And that's because the acceleration functions kind of like an accumulator, where we're going to be adding multiple forces to it over time. And we want to reset those in between every frame so that things don't get completely out of control. So let's test this acceleration idea. We're going to add another function here. We're going to call it apply force. And this one is going to be, the job for this function is going to be take a force vector and apply it to the agent. And all it's going to do for now is going to say agent.acceleration.add force. So add the force to the agent's acceleration. So let's give this a test here. We're going to create mouse press so that every time I click the mouse, I'm going to generate a new vector, and we're going to make that vector random, much like the one we did in create agent. Replicate that over here, and then we're going to say agent.apply force. We're going to say apply force and then agent and v. So we're going to say take this random vector we made, right, apply it to this agent's acceleration. So we can see that now every time I click, right, we're giving eventually this guy's going to leave the screen, so let's refresh here. We're giving it a push by adding a random velocity, right, a random acceleration, which then gets added to the velocity. And so it's getting randomly pushed over time whenever I press the mouse. Okay, so this is just for testing. The other thing we could do also that we did in at this stage that we did in previous examples is we could add the idea of damping to this simulation. So we could say, let's create a global variable. Let's call it damping. And let's set it to, let's say, 0.9. And when in our motion code here, what we're going to do is before we add the velocity to the position, we are going to multiply the velocity by this damping factor. So it's going to shrink the velocity over time, and it's going to cause our object to just stop on its own. And a damping of 0.5 is actually 0.9 turns out is actually quite a bit, because it's shrinking by 10% every frame, and that adds up rather quickly. So we could say, we could make it even higher. Come back. And notice it's not following my mouse at all, right? It's just random wherever I click. And then if we don't set any damping, we'll just keep that value at 1, and that just basically will have no effect. So now the object's going to move forever. It has no resistance, right? There's nothing stopping it. And as soon as that damping number dips below 1, what we're basically doing is like eating away. We're sort of chipping away at an object's velocity over time, so that if there aren't more forces coming in, eventually the object will stop on its own. So this is kind of simulating, in the real world, there's always a little bit of resistance or friction. Even the air, right, gives some friction. So if you don't have a constant acceleration, or if you're not constantly applying a velocity to an object, then it's going to stop on its own. So you could represent that using damping. So let's leave it at 1 for now, just so our objects just keep moving. But now we have the option to tweak that setting in our simulation. Okay. So now we know that apply force is working. I'm just going to delete this mouse press function. Now let's talk about creating our first behavior. It's going to be similar to what we did in week 2, but with some slight differences. We're going to approach it in a slightly different way. And that's going to be basically giving the agent the ability to seek or to follow a particular point on screen. So we're going to create a new function for this behavior. We're going to call that function seek. Yeah? And the idea is we're going to give the agent a target vector, and that's going to be where it tries to go. And then we're going to program a behavior to get the agent to move towards a given direction. So a good place to start here for our seek behavior is we know that if, so these are going to be positions. And if I want to get the vector that's pointing, say, between where this object is and let's say the mouse coordinate, right? If we represent it as a vector, in order to get a direction from one vector to another, we need to use subtraction. So we're going to create a new vector here. We're going to call it target direction. And that's going to be equal to, now what I want to take is the target. This is where I want to be. And then the agent's position, this is where the agent is. We're going to subtract the position from the target, but I don't want to modify this target vector. So I'm not going to write target.sub. Instead, I'm going to use this syntax, which is kind of taking a global subtraction function called p5.vector.sub, which takes 2 parameters, right? The vector I want to subtract from, and then the vector I'm going to subtract. So this translates to, target direction equals target minus agent.position. So that's going to give us a vector that points from the target towards an agent's position. And then we could imagine, we could apply this directly as a force if we wanted to, and then see what happens. So we're going to say agent target direction. So let's try this. So in draw, so now we're going to add some behaviors. We're going to say seek. So the agent needs something to seek, and just to make it easy to test here, we're going to use the mouse coordinate. Now the mouse coordinate is not a vector, so we're going to make it a vector here. We're going to create a vector called mouse. And that's going to be simply mouse x and mouse y. And that will allow us to use that mouse variable as a vector for our behaviors. So we'll say agent seek the mouse. Oh, I misspelled target direction here. Now we had a similar issue here in week 2, where it seems like it's working, but this target direction could be a huge velocity vector, right? Especially if our object is far from the mouse. So if we want to create an actual animation of this object, so we're going to have to limit how fast an object can go in our simulation. And we're going to represent this by adding another property to our agent object. So whenever I want to add detail, right, to our agent, I'm going to go to my create agent function, where I'm defining what it means to be an agent object. And I can simply just keep adding more variables to the agent. So this property, we're going to call it max speed. And that's going to be, I'm going to set it to 4 for now. That's going to be how quickly the object is allowed to move in our program. So we could say here, for example, we could limit an object's speed here. In our move function, we're going to say agent dot, we could limit it over here, or actually we could limit it in the seek function. So let's do that instead. we're going to take target direction, right? And we want to make it so that it goes to the object's maximum speed. So there's a couple of ways we could do this. One is we could use limit, but if it's smaller than that, it's going to be slower than max speed. So let's always go to the maximum speed. In order to do this, we're going to first we're going to normalize. Okay, so normalize means take the target vector and cut it down to have a length of 1. Okay? So now we can see we're always getting a length of 1, and then we're going to multiply by agent.max speed. Now we can see our agent is, going really, really fast, but not as fast as it was before. Okay? It's limited by maximum speed. Okay. So it turns out that if we just apply this direction vector as a force here, this is not a super interesting behavior. And it's just the arrow pointing directly from the object to the destination. Instead, we're going to add one more layer to this, and we're going to add this idea of steering, which is something that Craig Reynolds came up with. So when we talk about steering, what we want to do is instead of thinking of this direction as a force we want to apply right away, we're going to think of it as a target velocity. So our object has a velocity right now, and this is its ideal velocity would be target direction in order to point directly towards its goal. So what we're going to do is we're going to calculate, what would be the vector that would take us from our current velocity to this target velocity. And that's going to be another subtraction, okay, similar to the thing we're doing with positions. And that's going to become our steering vector, which means how much we need to turn in order to achieve this target direction. So we're going to subtract target direction, right? We're going to subtract the agent's current velocity. I have an extra parenthesis here. So that's going to be our steering vector. And then instead of target direction, we're going to apply this as a force to our agent. And now this is what happens. So this is a little bit more controlled, right? So in each frame now we're doing two things. First, we're calculating the direction vector between our agent and the thing we're trying to seek or follow, which right now is the mouse. And then once we have that direction, we're using it to sort of move our velocity by steering in that direction. So that's where the steering comes from. And we can further refine this behavior by limiting how much steering we're allowing our object. So right now it's pretty instantaneous, right? We get the full velocity right away. So what we could do also is we could limit the amount of steering force. Let's call this max force that we're allowed to apply whenever we're steering in a particular direction. So the steering force here we're going to limit, which means take the length of the vector, right, and cap it at a certain length or a certain magnitude, and we'll say agent.max force. So I'm using 0.1 here as the first one, and then you'll see that if we limit the force, our object takes a little bit longer to turn towards the destination. And we can create some more interesting behavior that way, or at least have a little bit more control. So the higher the force, right, if we have a force of 1, the higher the force, the quicker the object is allowed to turn towards the target. And then the lower that number, we can go really, really small here to demonstrate the extreme. You see that now we're turning very, very slowly, but still towards the target. So now the behavior can be a little bit more interesting because here it's going to overshoot here, and it's going to eventually turn around and try to make its way back to the mouse cursor, but it can't quite make it because we've limited its steering ability. So the reason we're creating all these different parameters is that down the road we have things that we can use to influence our simulation and give it a little bit more life, or we can choose to affect these agents in different ways. So I found a 0.1 max force here is pretty nice with what we're trying to do. The agent's going to overshoot, and then it's going to keep coming back. and we get this, this nice little behavior here. So now we've created a simple little behavior where we can seek a position, right? So try to aim towards a point on the screen, and we have a few parameters we can play with to affect that behavior. We can change the maximum speed at which the agent is moving. So for example, if I turn this to 1, right, now I cannot go faster than 1 pixel per frame, but I still have the same steering behavior. We could increase this to a really high speed, for example, and now this agent is moving much quicker, but its ability to turn is limited by max force, right? So there's lots of richness we can achieve in the behavior just by playing with these two values. Let's go back to 4. Okay. Now, one thing that's already starting to happen here is we have a lot of functions. So I'm going to make this code a little bit more readable for myself. This is something I like to do. We're going to put in little comments as dividers here between the functions, little comment lines. You know, they're kind of little dotted lines here, and or dashed lines. And I find when code starts to get a little longer and we start to have lots of functions that are building up, visually here, it's a little bit easier to tell them apart, like where one begins and where one ends. And as we scan through the code for the different functions, I find, for me anyways, that makes it a little bit easier to manage where things, sort of the start and end of different things, and kind of be able to visually see, okay, I have a function over here, I have another one over there. So it's just something I like to do. So for the last step in this example, we're going to bring in more agents. We're going to add our idea of a group here. Instead of having a single agent, we're going to create a group. So a group is just going to be an array, right? And what we're going to do is just change this program so that we're going to create agents over time. So I'm going to take that out of setup here. And then in draw, we're going to say if group.length is smaller than, let's say, 25 for now, we're going to make a new agent. Then this this agent is going to be added to the group. And then in here, we want to put this code into a for loop, because now we're going to be adding agents to our group array. So we want to write a for loop that's going to let us go through all the agents we've added to the group, and then apply our seek behavior, our render code, and our move code. And here I have to write let agent because I've deleted the global variable. And oops, this should be push. I still get confused with Java code sometimes. Okay, so group.push, not group.add. So now we can see, I'm going to refresh this here. So we're getting up to 25 random agents, right? So we start with none, and then in every frame, I could also decide to do like a little for loop in setup that would add all 25 at once. I like to do it like this so that they kind of come in over time, but we cap it at 25 here. So as long as the group length is less than 25, we're going to keep adding new ones. So this is a number we could tweak, right? If we increase this, and we would get 100 agents, you know, that could be interesting, but that might be too many for now. I'm going to leave it at 25. And we can see they have this seeking behavior where they're all kind of swarming around the mouse cursor. Now here, now that we have many agents, also if we wanted to, we could make this simple behavior a little bit more interesting. You know, we could think about doing things like, you know, we could randomize these per agent so that maybe different agents would go slower and some of them would go faster, right? So now they have different speeds, and maybe we could give them different, you know, turning ability, for example, so that some of them are more responsive than others, just to make, you know, the behavior looks a little bit more less like all the same. Now they all have some slight differences because these variables are per agent, right? They're part of the agent object. we can give them all slightly different attributes if we wanted to, just to make this a little bit more interesting. Okay, so to recap briefly, this is very similar to what we've done in week 2, with a couple of important differences. The main one being this seek behavior that's new from this week. So we've kind of introduced the idea of, in order to follow a point, we're not just going to only calculate the vector towards that point and then go in that direction. Instead, we're doing it in this kind of indirect way, where first we calculate the direction of where we would like to go, and then we modify our velocity by applying a force, right? That is a difference between where we would want to go and where we're actually going. So that creates a steering or a turning behavior that is going to take the object and turn it towards its direction, as opposed to just moving it straight towards it. And that leads to some slightly more interesting behaviors. We're also going to reuse that concept in the next lesson, where we're going to now start to talk about group behaviors. So now that we have this simple little setup here, the next thing we're going to be working on is having these agents react to one another and kind of behave within the group as opposed to only individually, right? So this seek function here only affects agents individually. We're not looking at the others at all. So that's going to be the focus of the next lesson. So we're going to talk about separation, keeping agents away from each other, and then programming some kind of basic, swarm or flock algorithm that it's inspired by, natural phenomena like a flock of birds or a school of fish or something like this, where agents are going to be influenced by the ones around them, and their behavior is going to be both what they want to do, but also what others around them are doing. All right, so I'll see you in the next lesson.